go there. And he told me that the conference was very nice. I mean, in person, of course.
Yes.
And his experience was very, very positive there.
I think he came in Brazil maybe 2018 or 2019. Possibly, I think it was two years before the COVID. Okay. I think. I guess it was in 2018. Mm-hmm. It was, of course, it was very good. It was in São Paulo.
Yeah.
São Carlos, it's good. But the virtual event, it's good because it's much more easy to have the keynotes, the participations of the keynotes. Because,
that's true. That's true.
Yes, do not have to travel. There are some advantages, of course.
Yes.
Of course, it's not the same thing, but there are some advantages.
I agree.
Yes. Gabriele, I'm just waiting a few more people.
Yes, sure.
Yes.
More rush.
Yes. Just check here. But of course, you are invited to come in Brazil, maybe in the next editions.
I will. I mean, I've never been there. There. Actually, I miss the South America, so yeah, I would like to come.
Have you been in ICSI in Buenos Aires?
Oh, right. Yes. No. In Argentina, yes.
In Argentina. Yes.
You're right.
Okay.
Yes, I've been.
Yes.
That's correct.
Okay.
Yeah. But it's the only time I went there.
It's maybe someday we'll organize an ICSI in Brazil. Someday.
That would be cool. Yes.
Yes. Maybe we'll have to find. First, you have to find some candidates to organize. Some crazy guys. Some crazy guys.
Yeah, you need a big team for it.
Yes.
Not trivial.
Yes. Gabriele, I think it's 9 o'clock. I think you can start.
Okay. So I'm going to share the screen.
Yes.
Okay.
Hello, everyone. Good morning. It's a pleasure to start the second day of Brazilian Symposium on Software Engineering. Of course, it's also a great pleasure to have here Professor Gabriele Bavota this morning as one of the keynotes at SBES. I'm also sure that most of you already know him by his papers and his high quality papers and very impactful papers. So, but I will just briefly here summarize his biography. He finished his PhD not a long time ago in 2013, University of Salerno in Italy, and he is now an associate professor at the Faculty of Informatics of the Università della Svizzeria Italiana. He has more than 140 papers in the most important software engineering conference and venues in journals, including distinguished papers at ICSI, FSE, and ASE, and also distinguished papers at SCAN, ICSME, MSR, and ICPC. And also in 2018, he received the ACM SIGSOFT Early Career Research Award. So thank you very much, Professor Gabriele Bavota, for accepting our invitation to be here at SIGSOFT this year. For us, it's really a pleasure and an honor to have you with us.
Thanks a lot. So I can start?
Sure.
Okay. So good morning, everyone. Welcome to this talk. Before starting, I would like to thank the organizers for inviting me to give this talk. It's actually my pleasure. And also thanks for the very nice introduction. So since I think that some of you don't know me, I'm going to spend a couple of minutes more in telling you something about myself, and then we go to the meat of the keynote that is about the automation of code-related tasks. Now, I know that we have the question time at the end. In case you don't understand something, feel free to interrupt me, okay? It's not a problem. As said, I'm currently an associate professor at the Software Institute of the Università della Svizzera Italiana. And wait, something is not working, okay. And in the bottom of this slide, what you can see is the name of some of my colleagues that are basically the other members of the Software Institute. I'm sure you know some of them because they are quite active in the software engineering research. The Software Institute is located in Lugano. That is a small and beautiful city in the south of Switzerland. Is very, very close to the Italian border. And what I do there is basically to direct my research group that is named CEART. If you're interested in what we do, you can have a look at the website, the URL that you find on the slide. But what I really care to tell you is that I have an amazing team of people that are these guys. As of now, there are 3 postdocs that are Emad, Bin, and Luca, and 5 PhD students that are Matteo, Antonio, Alejandro, Rosalia, and Tonsai. So everything that you're going to see today is the result of their work, okay? If you see something that you like, most likely this is the result of their work. If you see some idea that you find not very smart, maybe it's my idea, okay? But they are super good. So let me move to the core part of the keynote. We will talk about automating code-related tasks. And I decided to focus to present you 3 very preliminary works that we did. What do I mean with preliminary works? These are not works that, let's say, we didn't publish. But these are works in which we tackle a specific problem that is related to automating a code-related task, but we didn't obtain, let's say, very positive results. Okay, I don't want to say they are negative, but they are kind of okay. Why I decided to focus on these specific problems, on these specific works? Well, it's because I believe one of the goals of my keynote is also to give some of you maybe some ideas for future research. And I think in this area, there is a lot to do, okay? Because as I will show you, we are very far from having something that it's actually useful for developers, okay? We're gonna talk about the 3 main topics that are the recommendation of code components, which means you have a developer performing a certain task, and you want to recommend code components that are relevant for the task at hand. So you have a sort of code base, and you want to retrieve from this code base relevant code components. The second is the generation of code, the automated generation of code, which is something a little bit different because in this case, you don't recommend code that already exists from a code base, but what you do is to generate code. So while the developer is writing code, you try to autocomplete it, okay? Is what we have as code completion in IDE, just a little bit more advanced. And finally, the automation of code review tasks. So as you know, code review is central to the development process nowadays. It helps in improving quality, but it also costs a lot, right? So it makes sense if we can automate some specific tasks of this process. So I will start with the first work. Let me introduce a little bit the context, okay? We are in the context of source code recommender systems. And if you look at the literature, I classified these recommender systems, let's say, in 3 families, okay, but other classifications are possible. So the first one are the standard code completion that I mentioned before. So the developer is writing, and you try to predict the next few tokens that they are going to write. And in this field, there are the deep learning techniques that are on the rise, okay? In the slide, you can see one of the many papers that have been published recently. This is an excellent work. If you want a pointer reference for this specific task, this is a very good paper. The second family is what I call code to natural language translation. In other words, you have the developer writing in natural language, describing in natural language a piece of code that they need, and then there is some machinery that can, let's say, translate this piece, this description, this natural language description into a piece of code, okay? Can generate code based on the description. And the last one is code retrieval. What I said at the beginning, you have a code base, you have, for example, a developer describing in natural language what they are doing, and then from this code base, you try to retrieve code components that are relevant for that specific task, okay? Now, if you look at all these techniques, you can notice that they all assume that at a certain point, the developer will, let's say, ask for help. What does it mean? For example, in the case of natural language to code translation, the developer describes the code that they need, and then the machinery synthesizes the code. In the case of code retrieval, you describe the task that you have attended in natural language, and from this code base, you retrieve something, right? You retrieve a relevant code components. So what we wanted to do was something a little bit different. What we tried to do was to learn code implementation patterns. What does it mean? Well, the basic idea is the following. If you look at how software is developed nowadays, very often, if we are, for example, in the context of an object-oriented system, what you have is that if you have to implement a new feature, what you do is to implement a sequence of methods one after each other, right? You implement them one, then you implement them two, then you implement them three, and so on. And I mean, this is also driven in some way by modern frameworks that we use, for example. If we get, for example, Android, for many of the features that you can implement in an Android app, there are great tutorials in the official documentation that tells you, for example, how to select the current place on a map, okay? And what they tell you is, okay, first of all, you need to implement a method to check whether you have the location permission, and then you need to override this method on request permission result, and then there is another method to override, and then there is another one, and so on. So basically, you are following a certain implementation pattern that in this case is dictated by the specific framework APIs that you are using, okay? So going back to the original question, what we wanted to try to do was, let's assume that I have a tool that can monitor what the developer is doing in the IDE and can identify that the developer implemented method M2 and then implemented, sorry, M1 and then implemented method M2. Can we predict that next the developer will implement method M3 and 4, and can we recommend these methods, including their code and everything, so that the developer saves time, okay? This was the basic idea, and this is the basic idea behind this work that has been published last year at ICSI. And now I will briefly describe to you how the approach works, the results that we got, and then we will use these findings in order to think a little bit about what we learned and what are the challenges here, okay? So our idea was, let's start to experiment this approach in a quite narrow context. So we decided to try to learn code implementation patterns in Android apps. Why? Well, two reasons. First, as I said, we wanted a narrow context. Why? Because if you cannot observe repetitive implementation patterns in a narrow context, well, it's very unlikely that you can observe repetitive patterns in a broader context, such as all the Java applications, okay? And second, Android is heavily based on APIs. So if you need to implement a feature, probably you need to rely on certain APIs. So it's more likely to observe repetitive implementation patterns across different apps, right? So we can learn from this data. So basically, the whole point was, if this thing is not going to work on Android, will not work in a more general scenario. Okay, so let's start with the easy stuff. So the first thing that we had to do was to collect Android apps from which we can learn these implementation patterns. So this was our first step, and I'm pretty sure that this is something that many of you did when running, for example, MSR studies, right? What you have to do is to select your subject systems. So what we did was to pick on GitHub all the systems, the repositories written in Java, having more than 100 commits. Why? Because, as I will show you, we need a decent change history to learn code implementation patterns. And we made sure that these were Android apps, okay? We collected around 21,000 repositories. Now, let me open a short parenthesis. Since this is a task that I'm sure many of you have to do, like the selection of the subject systems, what we did in my group was to develop this very simple tool that you can find online. There is the link in the bottom right corner of this slide. And what you can do with the system is to search for GitHub repositories that meet specific selection criteria. For example, you can say, I want all repositories that are written in Java, okay, that have more than 100 commits, more than 100 issues, more than 100 stars, and that are not forked repositories, okay, so there are not copies, let's say, of other repositories. And in a few seconds, you can get your results, okay? You get, like, in this case, 3,000 repositories, but we are continuously mining and updating this data, okay? So we have data about around 1 million repositories in 13 different languages, and I think this tool is very handy if you do research in MSR. So feel free to try it. It's also open source, so there is the GitHub repository. You can open issues if you find something, or if you want to propose new features, or you can just join us and improve this tool. Okay, done with the parentheses. So we have these 21,000 Android apps, right? The next step was to identify methods added in commits. Why? Because our assumption is the following. If a developer implements a set of new methods in a specific commit, then probably these methods are related one to each other, are related to a specific implementation pattern. So we can learn something from this pattern, okay? So what we did was, okay, let's take the history of each app. We have the commits. From each commit, we focus on the added and modified files. We exclude the deleted files. Why? Because you cannot have new methods implemented in a deleted file, right? Either it's in the added or in the modified. So for the added and modified files, we run on them a Java parser, and we extract the newly added methods. Okay, so we have this information for each commit. We mined 2.7 million commits, and then we excluded all those that added less than 2 or more than 10 new methods. Why? Well, less than 2, because remember, we want to learn implementation patterns. So we want to learn that if a developer implements method M7, then the developer is also likely to implement method M9, okay? Just saying. So if you have less than 2 methods, 2 new methods implemented in a commit, there is nothing to learn there for us, okay? Why we excluded the commits adding more than 10 new methods? Well, because we want to kind of exclude tangled commits in which developers do many different things. We want to extract the implementation patterns that relate to a very specific task, okay? So at the end, we collected around 850,000 commits that are valid, that add between 2 and 10 new methods. So this is the information that we have as of now. The next step is the clustering of similar methods. Let me explain why we need to cluster similar methods. So the information that we mined as of now, the one that I tried to explain, we have this set of apps, right? That are 21,000, and we have this set of 850,000 commits. And for each of these commits, what I know is the set of new methods implemented in that commit, right? So for example, I know that commit 2 implemented a new method named M4 and M5, and commit 3 implemented 2 new methods named M6 and 7. Now, if I want to mine implementation patterns, if I want a pattern, this is something that appears several times in a dataset, right? By definition. So this means that I need a way to understand if in different commits, possibly coming from different apps, I have the same set of new methods implemented. What does it mean? It means that, for example, I need a way to understand if M4 and M5 represent the same implementation pattern of M6 and 7. So let me show you an example to clarify this point. Let's assume that these are the 2 commits that I have. So on the left, you see the methods implemented in the first commit, M4 and M5. I'm going to show you M5 in a second. And on the right, you have M6 and 7. So if you compare M4 and M6, that are the 2 commits, the 2 methods, sorry, that you see now, you will see that they are identical. They are type 1 clones. The only thing that changes is the name, but both of them implements a feature that allows you to check if the external storage is writable in Android, okay? And if I look at M5 and M7, again, they are similar. They are not type 1 clones, but they implemented the same feature. They check if the external storage is readable this time, okay? So this means that these 2 commits that come from different apps and that implement methods having different names, they basically represent the same implementation pattern, okay? So we need a way to compare all the new methods, the newly added methods that we mined across these 850,000 commits. And we need to decide which methods represent the same implementation, represent the same feature, basically, are clones, okay? So what we do is to build this weighted graph where each node represents one of the newly added methods that we mined, and the weight on the edge connecting two nodes represent their similarity on a scale between 0 and 1, where 1 means that they are exact clones, okay? We use a clone detector to compute this similarity. Then what we do is to remove from this graph all the edges having a weight lower than 0.9. This is a parameter that we tuned. The details are in the paper, of course. But at the end, what we get is a set of connected components that represent different clusters of methods, okay? So within each cluster, the assumption is that I have methods implementing the same functionality, even if they come from different commits of different apps, okay? So what can I do with this information? Well, if you remember, we had the data in this format, right? For each app, for each commit, what we had was the set of methods, of new methods implemented in that commit, okay? And I wanted a way to understand that N4 and 5 represented the same implementation pattern of N6 and 7. So now that I know to which cluster each added method belongs, what I can do is to replace its name, let's say its identifier, with the ID of the cluster it belongs to. So now I can see that commit 2 and commit 3 basically represent the same implementation pattern, because they both implement a new method from cluster C1 and a new method from cluster C2, okay? So now I have my data in this format. For each commit, I know the methods that have been added, and in particular, the clusters to which they belong, okay? So once I have this data, what I can do is to apply on them a data mining techniques that is association rule mining. Now, I'm pretty sure that most of you know this technique. If not, it's not a problem, because what you have to understand is just the output that we get from this technique. So this is the input, right? We provide this information that we mine and that we process a little bit. And the output is a set of association rules. What is an association rule? Well, let me focus on this one, okay? Just one, but you get many association rules. So an association rule has a left-hand side and a right-hand side. Remember this terminology because I'm going to reuse it, okay? So in this case, what this association rule is telling us is that if a developer implements a method belonging to cluster C3 and a method belonging to cluster C5, then it's very likely that they are going to implement a method belonging to cluster C4, okay? So the left-hand side is what the developer already implemented. The right-hand side is what we can recommend based on what we observed, based on the left-hand side. And association rule mining also provides you with some proxies, indicators, if you want, of the quality, of the reliability of these association rules that are the support and the confidence. So the support is telling me that 0.5% of the commits in my dataset, and remember we have like 850,000 commits, so it's still a lot of commits, support this rule, which means that in 0.5% of the commits, the developers implemented a method belonging to cluster C3, a method belonging to cluster C5, and a method belonging to cluster C4, okay? The confidence is telling me that 82% of times that a developer implemented a method belonging to cluster C3 and a method belonging to cluster C5, they also implemented a method belonging to cluster C4, okay? So this is, in few words, association rule mining, and this is the base for our recommendations, okay? So once we build this set of association rules, we can recommend something to developers. In particular, we built this tool that is named Fierce, okay? And it's an Android Studio plugin. So let's assume that this is your IDE, Android Studio. Fierce is running in the IDE and is monitoring the code written by the developer. When it finds that a new method is added, this method is sent to the web service, okay? What the web service does is to check whether we know this method. In other words, whether we have a cluster that contains methods that are very similar to the one that just implemented by the developer, okay? If this is not the case, well, we have nothing to recommend, okay? We are done because we have never seen this method. If instead we find a cluster that contains methods very similar to the one that the developer implemented, what we check is if there is an association rule having this specific cluster as the left-hand side. Okay, remember the left-hand side is what triggers the recommendation. So it's what the developer implements. Okay, so if we don't find an association rule having this cluster as the left-hand side, again, nothing to recommend. Okay, otherwise we can recommend a method belonging to the cluster in the right-hand side of the association rule as the next method to implement. Okay, so the developer gets the whole method, the whole next method that they should implement. This is the user interface. So this is actually the graphical user interfaces of the plugin that you get in the IDE. So there is this sensitivity bar on top. If you move the slider towards low, it means that you want to receive less recommendations, but of higher quality. If you move towards high, it means you get more recommendations, but you also get more false positives. As you can imagine, what we do here with this sensitivity bar is just to say, if you move towards low, so you want less but higher quality recommendations, we increase the minimum support and confidence to consider an association rule as valid. Okay, so these are, let's say, better association rules. If instead you move towards high, we lower these thresholds for support and confidence. So we have more association rules, but these are also lower quality association rules. Okay. Then you see the methods that are circled with 2 in the UI are the methods that the developer implemented and based on which we are recommending the method that is circled with number 3. So this means that in this case, the developer implemented update location and start location update, and we are recommending get last known location. Okay. If the developer likes the recommendation, copy paste, and of course, we also put in the comment the source of this method, okay, from which open source Android app it comes from, so that you can double check for licensing issues. So to sum up, what we did, we mined 21,000 Android apps. We extracted the methods, the new methods added in each of their commits. Then we clustered together similar methods to be able to identify patterns across different apps. We run association rule mining, and association rule mining is used to recommend to the developer the next method to implement based on what they already implemented. Okay, so the basic idea behind this work, that I think it's an interesting research direction, is that what a developer is doing has a high chance of having been done by someone else somewhere else before. Okay. And I think there is a lot that we can do based on this specific statement that you see in the slide. Now, the obvious question that should be in your mind as of now is, does it work, right? So if you really want to experiment with this tool, I think the only way would be to run a controlled experiment and to see if the productivity of developers, whatever it means, increases by using your tool, okay? But this was done in pandemic times, so we didn't have the chance to do that. So we designed, let's say, an artificial evaluation that I will try to summarize. It's a little bit complex. Again, details are in the paper. My goal is to give you the general idea, okay? So if you remember, we have the history of these 21,000 maps. What we did was to split it into 3 parts. The first 80% training, which is basically where we learn the association rules, okay? This is where we learn what are the relationships between the methods, okay? The implementation patterns. Then we have 10% for validation that we use to tune the parameters of our approach. For example, the minimum support and confidence, the minimum similarity to consider 2 methods as part of the same cluster, and so on. And 10% for testing, which is we take the best configurations and we run them on the test set to compute the performance, the quality of the recommendations. Now, the question is, how can we verify if a recommendation was correct or not, right? This is the basic idea. Let's assume that we have 3 commits, either in the validation or in the test set is the same, because we assess the performance both on the validation to find the best configuration and on the test set to assess the performance of the best configurations. So we have these 3 commits, I, J, K, okay? And you can see, we know from the change history, what are the methods added in each of these commits, okay? We know to which cluster they belong, okay? So for example, in commit I, we have 3 new methods implemented belonging to cluster C1, C2, and C3, right? Then what we do is, okay, let's assume that at the time of commit I, the developer was using our tool, okay? What would have been the recommendations of our tool? So in this case, for example, from the association rules that we learned, we know that if the developer implemented C1 and C2, we would then be able to recommend C3, okay? So in this scenario, our approach would have been able to generate one recommendation, and we know that this recommendation would have been correct and would have resulted in the automated implementation of one of the three methods implemented by the developer. Okay, so the number of covered methods is 1. In this other scenario, we know that based on the association rule, our tool would have recommended the implementation of a method belonging to cluster C6. Why? Because we have the association rule that says if the developer implements a method belonging to cluster C4 and a method belonging to cluster C5, then the developer should implement a method belonging to cluster C6. But we know from history that this is not the case because a method belonging to cluster C3 was implemented together with C4 and C5. So in this case, FIRS, our tool, would have generated one recommendation, but 0 of these recommendations were correct, right? So 0 covered methods. So this is more or less the idea. Once you have this data, you can easily compute recall and precision. Okay, so recall is really the percentage of methods that you could have automatically implemented. The precision is how many of the methods that you're recommending are correct. Okay, so what were the results? Well, in short, these were the results. So the precision was around 70%, which means around 3 out of 4 methods we recommend are correct. But we are able to generate recommendations for less than 5% of the implementation tasks that we analyzed. So it means the recall is quite terrible, right? You are likely to get the recommendations, I don't know, 5 days out of 100. I don't know how to explain that easily, but very rarely, basically. So our tool is able to generate very, very few recommendations. So if we go back to our starting research question, can we learn code implementation patterns? In other words, can we predict what the developer will do next? Okay. Well, our experience is that it's extremely challenging to get good precision and recall, even if you mine a lot of data. Remember that we targeted Android apps, so you must expect worse results when you move to more general contexts, such as all Java applications. So basically, our conclusion is that we are still very, very far from having something acceptable that can be deployed to developers, right? But I believe that the idea of of learning implementation patterns, of predicting what the developer will do next, is a quite interesting research challenge, and I think there is very little about it. So I think this is a good research direction on which maybe some of you wants to jump. And yeah, we are keeping working on it, but there is really a lot to do about it. So this was the first part. Don't worry, the others are a little bit shorter, okay? Because now I introduced a little bit of context. So the second work I'm going to present to you is about the automated generation of source code, okay? So in this case, the problem is a little bit different because you don't have a code base from which you want to identify useful pieces of code to reuse. You actually want to generate code, okay? So you can think of it as code completion that we have in the ID, right? Where you get the recommendation for the next code tokens to write. So what we noticed, and this is a work that we started a couple of years ago, okay? So there are some news that I will discuss at the end. But what we noticed at the time was that most of the approaches in the literature were evaluating the models that they were presented, the approaches that they were proposing, in a very specific task that was predicting the next single token that the developer is likely to write. This means that you feed into your model an incomplete piece of code, okay, where you see this special mask token. We want the model to perform the prediction, and the model predicts, for example, sorted. Then you take this, you provide it as input to the model again, and you ask the model to predict the next token that is equal, and then you get false, and so on. Okay, so the model is asked to predict token by token this code. Okay, and we know from the literature that state-of-the-art techniques are very, very good in this specific task. Okay, But we asked ourselves, okay, but what happens in more challenging scenarios? Because, you know, if you think about predicting the next token, this is basically what we already have in the ID. Of course, we can improve a little bit the precision of the recommendations, fine. But I think this is something that already works very, very well, right? So what we wanted to understand is what happens if we ask these models, for example, deep learning models trained on a lot of data, to predict, to generate non-trivial code constructs, okay, several lines of code, entire code blocks, okay? So what we did was, let's take, for example, a piece of code, and let's mask several tokens that are needed to complete a statement. So going from here to here, okay, this is what we call token masking. Let's say standard code completion, just a little bit on steroids, okay, so longer predictions. Or what happens if you take the same piece of code and you mask entire blocks? Okay, so you ask the model to predict, in this case, what is the body of this if statement. This is much more challenging, right? So this is the basic idea behind this work that is, as of now, under review at TSC. So it's not published, but you find the preprint on arXiv if you're interested. And what we did in this work was basically to experiment with 3 data-driven techniques that are a standard n-gram model, a BERT model that is named Roberta, and a T5 model, okay, that is a transformer model. And I will show you the results of the T5, okay, because it's the one that achieved the best results, and I don't have time to go through all the results. Let me just briefly mention that the T5 is trained, as many transformer models nowadays, in 2 stages. You have a pre-training and a fine-tuning. So the idea of the pre-training, really to simplify, is that you have to teach to the model a language of interest. So in our case, the language of interest was Java. We wanted to predict the Java code, okay? So what you do during the pre-training is to perform a pre-training task to teach this language, the syntax of Java, if you want. So our pre-training task was very simple. It's a standard denoising task, which means you take, for example, a Java method, you mask randomly 15% of the tokens, and you ask the model to predict that, okay? Then, of course, during training, you provide to the model the correct solution, and this allows to adjust the weights of the neural net. So we did this pre-training on around 2 million Java methods. And then for the fine-tuning, we tried to fine-tune the model, the pre-trained model, to the specific tasks, code completion tasks that we wanted to experiment with, okay? I will present you 2 of them. There are more in the original paper. So the first one was the token masking, which means what we did was, sorry, I don't have it here, but was again to mask the final part of a statement, okay, but not a single token, many tokens. And the second one was to mask entire blocks, okay? So this means that from a single method, I get this instance, this training instance, but I also get this training instance, okay? So there are masked blocks that have different levels of complexity. And in this case, we had around 4.2 million instances for the training, for the fine-tuning. Now, what were the results, okay? So this is for what concerns the token masking. So we are asking the model to generate the last n tokens that are needed to complete a single statement. And n changes between 1 and 10. So we ask to predict the last token or the last 10 tokens, okay? You can see the number of tokens on the x-axis. On the y-axis, you see the percentage of correct predictions in that specific scenario. For example, when we only masked the last token. Now, what you can see is that our results confirm what is reported in the literature when it comes to very short predictions, right? Predicting 1 or 2 missing tokens, we are around 90% or even above. But as soon as the prediction task becomes more difficult, more complex, we go down to something like 10% with 10 tokens to guess, okay? And if we look at the block masking scenario, where we mask entire blocks of code, okay? In this case, as you can see, the number of masked tokens is a little bit higher because blocks can be composed by many statements. So you see the x-axis on a scale going from 5 to 50 at steps of 5, okay? And what you can see is, again, same trend when the block that we masked becomes very complex, well, we are around 3–4% of correct predictions, okay? So it's very, very challenging for these models. So what we learned, this was an I would say, non-trivial training that we performed on millions of instances. And the predictions were excellent when the masked tokens were very few. Okay, when predicting the very few next tokens, the developer is likely to write. But as soon as the prediction becomes non-trivial, well, at least the model that we tested with our training, with our architecture and so on, failed. Okay, it was not able to generate meaningful pieces of code. So if we had to write, let's say, a paper entitled something like automated generation of source code, how far are we? Well, the short answer for us would be very far. But I have to mention that since then, so after we submitted, after we performed our study, we all know, I think, that GitHub, OpenAI, and Microsoft presented GitHub Copilot that promises much, much more than what we achieved. I mean, I've seen the demos are impressive. I didn't have the chance to play with it, but I'm really curious to see what will happen by replicating our study with this tool. I'm sure it's much better than what we experimented with. But despite this, I still believe there is a lot to do also in this area, okay? Because when the generation of code deals with non-trivial tasks, well, these models still struggle a lot. And we will discuss this point a little bit more at the end of this talk, where we will talk about elephants in the rooms that we have in this field of automation of code-related tasks. Before going there, I have the last work I want to present you, again, in a few minutes. That is the automation of code review tasks, okay? So this is a work presented also in this case last year at ICSI. And it's a work done by one of my PhD students, Rosalia Tufano, as the first author. Of course, there are other authors. And the idea here is not to completely automate code review, because this does not make sense, right? We know from the literature that code review is useful not only to spot bugs, suboptimal implementation choices, but also to share knowledge among developers, to build team awareness and so on. So you don't want to completely automate code review. First, because it's almost impossible. Second, because it's a very important activity from a human point of view, okay? But what we noticed was that during a code review process, there is a lot of data that is generated. If you just take a pull request on GitHub, for example, well, you have the code submitted for review, then you have alternative solutions proposed by the reviewers, then you have the discussion between the author and the reviewers, so the natural language comments and so on. So if we want to simplify, let's say we have these two sides, right? We have the contributor and the reviewer. We have the contributor that submits the code for review. We have the reviewer that can recommend changes by writing comments in natural language. And then we have the contributor who can address these changes, create a revised version of the code. And of course, this is an iterative process that can go on and on until either the reviewer is happy with the code or the contributor gives up, right? Now, if you look at these three steps, during each of these three steps, there is a piece of data that is generated. So in step one, we have the code submitted for review, right? In step two, we have natural language comments posted by the reviewers. And in step three, we have the revised code implementing the comments, right? And if you mine open source repositories, well, you can build a data set of these triplets where you have the submitted code, a natural language comment asking for changes, the revised code implementing those changes, okay? So what we decided to do was to investigate whether it was possible to automate specific tasks using this data set, okay? In particular, we focused on two tasks that are on the two sides, one on the contributor side, one on the reviewer side. So on the contributor side, the idea was to create a model, a deep learning model, that can be used before even starting the code review process. In other words, the contributor submits to this model a code that they need to submit for review. And the model tries to predict what are the changes that will be output of the code review process and provides as output a revised code that implements changes that are likely to be required by the reviewer during the code review, okay? So this is an encoder-decoder model that takes as input the code submitted for review and tries to generate the revised code automatically. Okay, so we are not using the reviewer's comments here in any way. In the second task, instead, we wanted something that a model that can take as input the code submitted for review and a specific natural language comment asking for a specific change. So this is something that the reviewer is asking. And the model will take care of automatically implementing this change that has been required by the reviewer. Okay, so again, it outputs the revised code, but in this case, it has two inputs. So we have two encoders in the model, and the output is the same. But this time, the goal is to implement a specific change recommended by the reviewer. Now, again, there are many details in the paper, but this is not the goal of this talk. So what were the results, right, that we got? So let me start with the first task that, if you think about, is the most challenging. Why? Because the model only gets as input a code submitted for review without any additional information, and it has to guess how it should be modified before the code review process, okay, in order to already implement changes that are likely to be requested during the code review. Now, we computed many results. I will not focus on BLEU and Levenstein distance just because I believe this data is very difficult to interpret, to give a meaning to these numbers, okay? I will focus on what we call the perfect predictions. What are the perfect predictions? Well, if the model is able to provide us output exactly the same code that was output of the manual code review process, we say that this is a perfect prediction because the model predicted and implemented the changes that then have been required during code review. What you see in the first column, the beam size, to simplify, let's say, is the number of attempts that the model is allowed to perform. For example, beam size 1, it means that given a code as input, it can only generate one possible solution. Beam size 10, it means it can generate 10 possible solutions. So it's more likely to guess the correct changes, right? Because it has 10 attempts, let's say. So as you can see, the percentage of perfect predictions, these are instances from our test set in which the model managed to implement the correct changes. It's quite low, right? We go from 3 to 16%. So this thing is able to work, but in very few cases. In the second task, that is a little bit easier. Why? Because we provide to the model the code submitted, as well as a specific natural language comment that is asking for a specific change. Okay, this is a comment posted by a reviewer. And the model has to implement that change. So these are the results. Again, let's focus on perfect predictions. As you can see, now we go from 12 to 31% of cases. So much better, still very few instances, right? Now, when we got these results, we were like, well, you know what? It's not a lot, but it's interesting. I mean, this thing is able to learn some change patterns that happen in code review, right? So we were a little bit skeptical. And what we said was, you know what? Let's manually analyze all the perfect predictions generated by the models. Because in this way, we understand what the model was actually able to learn, right? And this is what we found. So you find that the whole taxonomy of changes, of transformations, let's say, that the model was able to learn in the paper. But to give you a quick overview, basically, these were very small and simple changes, okay, as kind of expected. So we have a bunch of refactorings, like, for example, simplifying an if condition, removing an unneeded null check, or even changes that just affected the readability of the code, like adding the this keyword somewhere and so on, okay? And there were also a bunch of behavioral changes, including, for example, bug fixes, okay, like wrong if conditions that were fixed. So there were some interesting changes, but what we noticed was that, I mean, we are still very, very far from automating more complex changes. So while there is still a very long way to go, we are working still a lot on this specific problem of automating code review related tasks, because we believe there is a lot to do. There is a lot of margin for improvements. And if you like this research topic, I really invite you to join forces, because really we are so far from a good solution that there is a lot to do. So it's a very exciting research, in my opinion. So now I presented you these three, as I said, quite preliminary works, right? This was done on purpose. Because now I want to discuss with you a little bit what are the elephants in the rooms that we have in this field, in the field of automating code-related tasks. And this is something that we learned from our papers, okay, so while working on our papers, and also from some interesting studies that have been presented in the literature and that I will mention. So the first problem I think that we have is that we tend to simplify a lot. What I mean is that we want to target a problem, we simplify it a lot because we are not able to tackle the tough instances of that problem. And at the end, I'm not even sure we are still addressing the starting problem, right? And as an example, I will use the paper that I just presented to you, automating code review activities, right? Because there are some details that I didn't tell you. So if you remember, I showed you this data set of triplets, and I told you, okay, we had, I mean, I didn't tell you, but it was in the slide, we had around 17,000 instances in our training set, okay? Now, at the beginning, actually, we had 200,000 instances, more or less. So we were very happy about our data set because we were like, well, you know what, we can learn a lot from this data set. Of course, you find everything in the paper. But then we realized that we had to discard many of these instances. Why? Well, for different reasons. First, for limitations of our approach, because, for example, our approach relied on code abstraction. Now, I don't have time to go there, but the fact that we relied on code abstraction didn't allow us to use many of the instances that we mined, okay? So we had a number of filters that we had to apply to this data set. I will just focus on one of them just to give you an idea. For example, we noticed that the model was really struggling to learn anything concerning instances, which means pieces of code that were longer than 100 tokens. Now, 100 tokens is not that little, but it's not a lot, okay? It's a standard method, let's say a few lines of code, like 5, 6 lines of code, something like that. So we had basically to exclude from our data set all those more complex instances, and we really focused on the simple instances. And at the end, we ended up by applying all these filters that are described in the paper with only 17,000 instances that have been used in our work. And I mean, this explains why at the end, we were only able to address the very simple code changes that are implemented in code review, right? So we are not really targeting any more code review, but we are targeting the simple part of code review, which I'm not sure is what we wanted at the beginning, right? And of course, now we are trying to do better, but this is an issue. If we think to the work that I presented about code completion, code generation, let's say, right? What I told you is, okay, if you try to predict 1 or 2 tokens, these techniques are stellar, okay, they're excellent. But if you try to generate non-trivial pieces of code, well, they fail, okay, they don't work. So if you work in this area, I think now we are quite good in predicting 1 or 2 tokens. Let's push forward, okay, let's target the real challenge. Let's try to really speed up code implementation, because otherwise it's basically what we already almost have in the IDE. And you know, there are also excellent studies in the literature that basically discuss this point. This is an excellent paper by Liu et al., published at TSC. And what they show is that if you take techniques in the literature that try to generate a piece of code starting from a natural language requirement, well, if the requirement is very simple, these techniques kind of work. But if the requirement is a little bit more complex, okay, let's say it's not trivial, these techniques do not work at all, right? So again, are we solving the problem that we targeted? Probably not, right? So this is the first thing that I think as a community working in this area, we should try to improve. Of course, it's fine to do a first step in the simpler scenario, but then we should not get stuck in the simple scenario. We should try to increase the complexity of the problem that we address. The second one is that we rely a lot on quantitative data, but from my experience, this is really not sufficient, okay? When you are working on the generation of code, on automating code-related tasks. Why? Because you just get a number, but you don't understand what your technique is able or is not able to do. And again, there are great works in the literature that show that. I will mention one of them, that is this work by Gross et al. At the ESC 2020. And what they do is to observe something very interesting. You know, there is this line of research about generating a comment starting from a code, right? And many authors, many researchers address this problem as a translation problem, which means this is code to comment translation, right? You translate source code into a natural language comment, which is fine. This means, however, that if this is a translation problem, it means that it's similar to natural language translation, for example, from Italian to English, right? So if this is true, this means that you can reuse the techniques used in this specific field, natural language translation, and you can also reuse the experimental setting that they have. For example, you can use the metrics that they use to assess the quality of the translations, like, for example, the BLEO score, right, that we use. Well, what the authors show in this paper is that if you use the BLEO score in these two problems, okay, like code comment translation and natural language translation, well, the BLEO score provides you with very different information, okay? The two problems are not as related as they seem, okay? So every time that I read a paper or I review a paper that says our approach improves BLEO score by 4% over the baseline, the only thing that I have in my mind is a question mark, because I'm not able to understand what this means from a practical point of view. What can your approach do that the baseline cannot do, right? So look at the predictions. Try to tell the readers of your paper what your approach can do that the baseline was not able to do. Okay, this is important. And even if you don't have a baseline for comparison, but try to understand where your approach succeeds and where it fails. That is, for example, what we did with the automation of code review, right? We were kind of surprised to have like 10%, I don't know, of correct predictions. But then if you look at what the model was able to predict, well, what we have seen are very simple changes, right? So this tells you something, and this tells you something that you can describe in the paper that is interesting for the reader. Okay, don't only target, let's say, the good results, because there is a lot to learn from the negative results. Next one, assumptions, which means I think several times we develop techniques based on our assumptions as researchers, but we don't know if this is really what developers want. And let me give you a concrete example, again, that concerns my papers. So the one that I present you as the first work, right? Predicting the next method the developer is likely to write and provide to the developer the complete next method. So the question that I had is, would developers use such a recommendations? Because I'm recommending an entire method, right? And of course, these methods, once integrated, could completely break the compilation because it comes from a different project. Maybe it uses a different coding style, different names for the identifier. So even if it's related to what the developer is doing, maybe it's more, let's say, a pain for the developer to use my recommender system rather than the benefit that they get. So I'm not aware, for example, of studies in the literature, or, well, there are a few hints, but there is no comprehensive study that really says what the developers are looking for when it comes to source code recommender system, right? What are the characteristics of code recommender systems that are useful for developers, that the developers really want to see implemented? So this is, I think, another interesting research direction. And last but not least, then I promise I'd conclude. We are learning a lot from open source projects. This is valid for approaches that recommend code components, like the one I showed you to recommend the next method. These are methods that we take from open source projects. This is valid for deep learning techniques that are trained on open source projects. And if you have an open source license, many times you can reuse that code in other open source settings, but you cannot reuse it for commercial purpose, for example. So what happens to these models that are trained on this data? Because, yeah, you can say, well, but they are generating code, they are not copying, right? It's true, but still, they were trained on program activities, if you want, performed by open source developers. So is this fine? Is this not fine? I think we have a gigantic hole in open source licenses on which I think you can do a whole PhD, okay? Because there are a lot of open questions about this point, and I think this is something that sooner or later we will need to address, especially considering tools that are proposed, that have been proposed, such as, for example, GitHub Copilot, right? That probably will be used by several developers. So it's interesting to understand what are the implications there, I think, from a licensing point of view. Okay, so I'm done. I just want to reiterate again that what you have seen is the work of these guys. Okay, the three works that I presented in particular are done by Tensai, the first one, by Matteo, the second one, and by Rosalia, the third one, with the help of the postdocs. And yeah, if you're interested in more work that we do, you can also have a look at the page of the main project on which we work. That is a project funded by the European research community that is named DeVinta. And just to summarize, so that you have, let's say, pointer to start the Q&A, I presented you three works. The first one on recommending the next method to implement to developers. And what I showed you is that it's very challenging to learn code implementation patterns. The second was about generating code in non-trivial scenarios, right? And what we found out was that at least the models that we trained were not that smart when the generation required complex code constructs. And the last one was the automation of code review activities, right? Again, I showed you some very preliminary results. And then we discussed the four elephants in the room that we have in this field. But I think the single message that I wanted to give with this talk is that the automation of code-related tasks is a very exciting research field, at least for me, but there is really a lot to do. So I think it's a very exciting area in which you can contribute a lot. And if you're interested in some of these works, feel free to contact me via email. And last thing I wanted to mention, for all the works that I showed you, there is a comprehensive replication package that you find linked in the paper, where you find the code. So the first tool, for example, is even open source. You find the code to train the models. You find the data sets that we use to train and to test the models. You find the scripts. These are all repositories on GitHub. So if you have issues, feel free to open an issue. We try to reply as fast as we can. And yeah, that's it on my side. I'm ready to take your questions, and thanks a lot for listening.
Thank you very much, Gabriele, for this very insightful, great talk. I think it's a really nice combination of novel ideas and at the same time very practical ideas. So we'll have time now for some questions. You can use the chat and also the microphone to make the questions. We already have two questions here. There is one question by Rodrigo Bonifacio. Thanks for the great talk. Any tips on how to avoid assuming that a new brilliant technique is everything developers want? Should we work closer to the industry? Do you see any negative implications with that?
Okay, thanks for the question, Rodrigo. So I think the question has basically two parts, right? The first one is how we can avoid the strong assumptions, let's say. I think there are a couple of things we can do. First, you know, we have, for example, many surveys in the literature. I haven't seen a survey with developer asking what the developers actually want from these tools. So this is something that could provide some evidence for the community. For your own research, of course, you can try to talk with developers, but this is not always easy. I mean, for example, I can tell you during my PhD, it was quite difficult to get access to developers. It became a little bit easier during the postdoc for different reasons, okay? So, but if you have access to developers, I think this is the obvious answers, right? Try to have a chat with some of them, try to understand what are their problems, try to understand where automation can be injected. Because as I mentioned when I started talking about the code review work, it does not make sense to automate everything, right? You want sometimes as a developer a helping hand on some tasks, but other tasks are really human-centric, right? You need the human that takes care of the task. So I think this is one part. The other part is if I see drawback in working with the industry, in close contact with the industry. No, I don't, but at least my experience is the following. When you start a new research thread, I'm not sure you want to immediately test your preliminary solutions with developers because, you know, they are dedicating you their time and you want to be sure to have something that at least to a certain extent works. So my suggestion is first try to design an artificial evaluation, such as the one that I showed you based on the change history of systems. Then try to do a small controlled experiment with a few developers that maybe you know and that can give feedback. And then you move to a more realistic setting with industry. But this is just my approach. Okay, I know that there are researchers that start working directly with industry. So I don't see drawback if you don't basically waste their time with solutions that you know from the beginning that are very unlikely to work, okay? Because, I mean, they are dedicating to their time.
Thank you, Gabriele. There is now a question by Ingrid.
Okay.
Hi, thank you very much for the great and inspiring talk. So I have a question regarding the 5% recall that you said in the beginning, in the first part of your presentation. So I assume that reviewer tool would say, oh, this is not enough. But if we really think, if you have GitHub Copilot, usually, like I saw some demos, it shows usually recipes of how you use certain API with some parameters to do something. But you were trying to predict the next method. And like coding up to now, it's not something really automated, because when you're implementing, you are implementing something that is tailored to the requirements of the application, the requirement you are implementing. Right. So I wouldn't expect that like you would achieve high recall for predicting the next method, because applications are different. So do you really think that we are going to achieve high recall? Because for me, automating 5% of the tasks of a developer is already good, because it's less work you need to do by yourself and manually. And this actually reminds me what happened in the recommender systems area, that in the first decade of this millennium, they were really focusing on precision and recall. And then in around 2010, there was a paper called Beyond Accuracy, Evaluating Recommender Systems by Coverage and something else. And then the people started to see, oh, it's not a matter only of maximizing metrics, but we need to think about novelty and these other aspects. So what's your view on that? Do you think that we are simply in a moment where software engineers are excited with machine learning methods and are not really focusing on solving actually the problem?
So Ingrid, thanks a lot for the question. I mean, it's super interesting, and I agree. I think you touched many interesting points. The first one was the reviewer 2 point, which I completely agree. I mean, I know reviewers could complain about those results, but yeah, I think one of the important thing is to be open, right? To say this is what we got, and it's less than 5%. So is less than 5% bad or good? It's difficult to answer. Let me explain why I think it can be improved, and it's not a very good result. Because when you target a narrow context, such as Android apps, it's true that you have different systems, okay? Different applications. But it's also true that they are all built on top of the Android APIs, okay? So if you need to perform a specific task, like, for example, showing something on a map or activating the Bluetooth or whatever you need to do, well, there are a bunch of APIs you depend on. So there are a bunch of APIs that you must use in one way or another, okay? You cannot just write it on your own. And so we expected that, okay, if we mine 21,000 apps, and if you have, for example, I don't know, 100 apps that are navigators, right? That so use GPS, use the map and so on, they will share something. So they will share a set of functionalities. And maybe when developers implement these functionalities, they follow a similar path, a similar pattern, because they need to implement methods that exploit the same APIs. Okay. So honestly, I expected more. But if you look at the general context, and if you say, okay, we achieved 5% for all Java applications, then I kind of agree with you that 5% is already impressive, okay, because it's not trivial. So this is my view, but in general, I think it's, you know, if you are able to predict what the developers would do next, and now, of course, I showed you an example at method level, right? But this can be done in many different ways. It's just the idea of predicting what's next. I think there are a lot of implications because you can recommend like frameworks to use, you can recommend useful documentation, right? If you're able to understand where the developer is going with implementation tasks. So it's not only about generating a recommending code, it's really to understand where they are going to recommend the pieces of information that are useful. And in that area, I think there is a lot to do. The last point that you mentioned, if I'm not wrong, is should we focus less on recall precision and consider a little bit more other aspects, such as the novelty and so on? Yes, I mean, this was my whole point about don't limit yourself to quantitative data when you try to understand what your technique is able or not able to do, right? For example, I would be very happy to see, you know, I mentioned it briefly, this code to comment translation problem that is tackled in the literature. I never worked in that area, but there are great works. And if you look at the techniques that are in the state of the art and you look at the overlap between them, the overlap, I mean, the cases in which they succeed, okay, they mostly work on the same instances. So there are some instances that are easy to generate, but I would be very happy to see a new approach that only works in 3% of cases, but this 3% is something new, right? Are instances that other tools are not able to support. So in that case, you get a 3%, but you're solving part of a problem that has not been tackled by other techniques. So yes, I think this is very important. Don't just look at numbers, but understanding what we are getting out of a new recommender. I hope I answered.
Thank you.
Thank you for the question. Thank you.
Thanks, Gabriele. We have a new question here from Delano. Do you want to make the question, Delano?
Yes. First, thank you, Gabriele, for the amazing talking. It's a super interesting topic. And my question is like a extension of the question of Ingrid. When you say that the data, the amount of the data is not enough, what do you want to say is like maybe if you have more context in the data, it could help to classify better, to have more accuracy. For example, if you have more data, structured data and label data, could have more context in the data and help to recommend better what the next method or the next thing. I don't know.
Yeah, okay, thanks for the question, Delano. So if I understood correctly, what you're asking is if I think that providing more context to the recommender system, whatever the recommender system is, could help in the recommendations. So the answer is yes, but this is not something that I think. This is something that for which there is evidence in the literature. Let me mention a simple example that is related to what I presented. So these techniques to generate code, right, the deep learning models. So there are works that show that if you have a multimodal representation of the code, what does it mean? That you not only provide to the model the code as a sequence of tokens, so as text, let's say, but you also provide to the model the AST of the code. You also provide to the model, I don't know, dependencies that it has towards other components. The performance increases, right? The prediction accuracy increases. And I think it's similar for the first recommender that I showed you. For example, if together with the new methods that are implemented by the developer, you can provide, I don't know, the description of the issues in the issue tracker to which the developer is assigned in that moment. Well, for sure, this can help the tool to understand where the developer is going, and maybe it can help in the prediction. So I think this is something that is very promising for the future, to try to provide more context to these recommenders, but it's not always trivial because, for example, if you use deep learning models, if you start having very long inputs, then the training time becomes super long. And you know, if you have, of course, if you are Microsoft, if you are OpenAI, this is not an issue. But if you have a PhD student who has to perform a work by training a model, you have certain constraints because he cannot train the model for 1 year, right? He needs to get something, he needs to see something otherwise. And so yes, the answer is yes, but it's not trivial, okay? It's you add context, but then you add also complexity.
Thank you.
Thanks for the question.
Thanks, Gabriele. We still have time for more questions. Delano, it's all right. You can ask in the chat or using the microphone. Gabriele, I have some questions. In the first work, the FIRS tool, if I understood it correctly, the idea is to start by mining the methods that change together in the same commit. Okay.
That are added together. These are new methods.
Yes, that were added together. Do you think it makes sense to also consider methods added in the different commits, for example, in commits making this in a small time window? And do you think that this can somehow improve the recall of the recall results?
So excellent point, because this is something that actually at the beginning we wanted to do. Okay, so this was on our agenda to say, well, you know what, it's true that a commit is a cohesive set of changes most of times when it's not tangled. But then if you have two very close commits by the same author, right, maybe with similar commit messages, well, probably this is a single implementation task, right? We didn't do that for one reason. First, we were unsure about what to use as a threshold to say, okay, these two commits are quite close, right? What is quite close? Is 5 minutes? Is 6 hours? And the second is that we thought that if we, by focusing only on specific commits, it was less likely to get false positive recommendations. So we decided in some way to sacrifice a little bit recall, but to get more precise recommendations. So I agree, this could help in increasing recall. It's just that, you know, there are all these open questions then to answer.
We have a question now by Rodrigo Andrade. Hi, Rodrigo.
Hi, Marco Tulio. Thanks for the talk, Gabriele. I also added the question in the chat, but I opened the microphone to make myself the question. Regarding your second presented work, what are possible strategies to feed the AI with the goal of predicting blocks of code? Because we see that in some cases it could be very challenging and not intuitive.
Okay, so what you want to know is basically, I showed that the results are very poor from complex blocks, how we can improve these results. This is the question?
Sure.
Okay. So I think there are many different aspects. I will basically skip the trivial ones, which are, in my opinion, bigger models. Of course, if you adopt AI models that are bigger and bigger, they can learn more, okay? And the other one is more data. These are the two obvious ones, okay? So if you increase the training data set, it's possible that you're going to increase the performance. For what concerns the non-trivial answer, I think something that would help is what we just discussed. So to provide more context to the model, because for example, what we did was to consider the method as the context, which means that we take a method, we mask a block, we ask the deep learning model to predict that block, but everything that the deep learning model knows is that method. But it's possible that that method, for example, inside the block that we masked, uses another method in the same class, right? But the model has no clue that that method exists. So if you can expand the context and maybe provide to the model a summary of the class, a summary of, let's say, of what is its universe in the system, so the dependencies and so on, I think this would help in specific cases, because sometimes we notice that the model included, for example, invocations to methods that the model could simply not predict because we're not part of the context, right? So I think this is something that could help. And the other thing is we performed this study by using the most simple code representation that you can use, that is the stream of tokens. But maybe if you provide also more structural information, such as you know, the nodes in the EST, so you visit the EST, you put it on a single line, let's say, and then you provide it to the model, this could help as well. Of course, we decided to focus more on getting this first study to understand what happened, but I think there are a lot of improvements that can be done. And this is why I was mentioning that I'm very curious to see what happens by replicating our study, like really taking the same data set with the GitHub Copilot that I really expect to be state of the art, right? Almost the best you can get as of now. And then we can understand, okay, where we still need improvements. So I have one PhD student who is working on this topic, that is automated generation of code. And when GitHub Copilot was announced, he was like, okay, I'm done. I cannot go on with my PhD. But I think that this is not the point. Of course, you cannot compete in terms of models that you propose because they have computational power, they have access to all data. But then it's interesting to understand the way they are not able to perform well, right? And then we can try to improve in that area. Or anyway, what are the implications of using Copilot on programmers? Is the code that they write different as compared to the code when they manually code? I think there are a lot of questions in this area. So I don't think that the GitHub Copilot is going to put an end to the research in this field.
Okay, thanks for the answer.
Thanks to you for the question.
And Gabriele, I have two questions. I think the first one is a comment indeed by Nabor in the chat. Developers mostly think by analogy. Research should think by first principles. We should help them in a way they didn't think of before. Much easier to say than to do, of course. And just a comment on your excellent talk.
Thank you. Thanks a lot. So yes, I mean, this is a good point. You know, there is also this discussion about should we ask developer what they need or should we tell them what they need? And I mean, this is, I don't have an answer, so I'm sorry. But yes, open question, community can answer, but I don't feel in the position to say this is the way to go. It's both strategies could work. I think at least starting from their needs is important because this shows you if there are open gaps in the state of the art. So if we really have no support for something that they consider super important, right? But then, of course, yes, you can also, as a researcher, suggest a new way of doing things. And in that case, yes, it's the researcher that points to the solution. But yeah, it's a very complex question.
Okay, you can work on both fronts. Yes. It's possible. And there is also a question by Thais Buriti. The first study focused on similar added methods from different projects, but other studies investigate code changes to predict code changes at different levels, files, methods in a project. The first lacks recall and the second precision. Can we find a path between the two strategies to improve recommendations?
Okay, good point. So I think what's named Thais is mostly referring to the work, let's say, on logical coupling. So you change something, you need to change something else, which, yes, I agree, it's related. To combine both, honestly, I don't know, because in one case, you are interested in identifying what are the relationships between entities that are changed, but for very specific tasks, such as, for example, change propagation, right? You say, okay, I changed entity X, so you also, I can recommend, okay, you also need to change entity Y, fine. But in this case, you want to recommend the next piece of code, right? So you need to learn from code that is added. It's a little bit difficult. So I see that the two problems are related, but I think also the fact that we got very different results is probably due to the fact that these problems are less similar than they look like. So I don't have a good answer for that, but yeah, I see the point. It's interesting and I will think about that.
Okay, we still have time for, I think, at least one or two questions. More questions? Anyone can make question? Gabriele, I have one more question. Mm-hmm. I think you already mentioned a comment about this, but of course you have now GitHub, Microsoft, OpenAI, GitHub Copilot. I think they spent training the GitHub Copilot $12 million only in cloud to pay the cloud machines bill. What do you think is our role in this process as researchers? Do you think that, of course, maybe it's very difficult to compete with these major companies? And what's your reflection about how can we really contribute to have results, to a research agenda in this area?
So first of all, I think we should be proud as a community, because it's true that we have a GitHub Copilot, but it's also true that we had years of research on this topic, right, in the software engineering community. So I think when a product like this is presented, we should only be proud and say, okay, we were doing something that is relevant for big companies, right, that other companies see value in. So this is a good thing. As I said, my PhD students were a little bit shocked, but what I think it's important is that first of all, I didn't have the chance to work with this tool, right? So it promises a lot, and I think it's great. I mean, from what you can see, it's clear that it's great. But I really don't know where is the bar now. I mean, I know that it's much better than what we did. Okay, this is trivially given, but I have no idea where is the bar. So I'm not able to say if there is more research needed in creating better models. Okay, but what I expect is that also their model will fail in specific complex cases, and probably we can try to characterize what are the areas where even this super large model does not work, and try to understand which solutions we can define to address those specific cases that maybe are based on deep learning, but maybe are based on other techniques like mining and data mining and so on. And the other point that I also briefly mentioned is what are the implications of these tools? There, I think there is a research agenda that is open, because again, licensing, what are the implications? Or what about the learning process of developers? What I mean is, one thing is if you write the code by yourself, right? You write and write and write and you learn. But what happens if you get a recommendation and you just press tab? You say, yes, this is what I want. Are you really learning? So again, this is something that we don't know as researchers. Or is the quality of the code that you write with the GitHub Copilot better than the one that you write manually? Do you introduce more bugs? So I think there is really a lot that can be done. And if you are a PhD student in this area, I will not be worried, okay? There is a lot to do.
Thank you very much. I fully agree with you, because whenever we have a major result, it also opens many more opportunities for research that we didn't had these ideas before, these problems before.
Yeah.
So, Gabriele,
I think we got a new question in the chat.
Okay.
If there is time, I don't know.
Sure. It's the blue score. If the blue score is not a good metric to evaluate such models, what could we use to evaluate them? Test sets to evaluate the functionality of the generated code? Okay, good question. So first of all, test sets would be cool, but we tried is too complex, because when you work with these models, keep in mind that the data sets you are dealing with are millions of instances. Even if you only take the test sets, probably you have hundreds of thousands of instances, and you will not have test sets for most of them. So, and when you generate code, it's likely that you introduce syntax errors, so you cannot execute the test. So it's very unlikely that we will go there. Concerning if you want a quantitative metric, so the first one that I recommend, that I think is the easiest to interpret, is just percentage of correct predictions. So you mask part of the code, you ask the model to generate, you compare the code, the generated code with the reference one, and you get a percentage. This at least tells you the percentage of times in which your model was able to correctly generate the code, okay? However, there is a problem. A problem is that this percentage of correct predictions is a lower bound of the performances of your technique. Why? Because what we observed is that many times these tools are able to generate, to recommend a piece of code that is slightly different from the original one, but functionally equivalent. So if you rely on perfect matches, right, the prediction is equal to the reference code,
you will lose a lot of these instances. So you are let's say, underestimating the capabilities of your model. So my suggestion is, first, correct predictions. Second, take a sample of the wrong prediction, like for example, 500, 1000 instances, manually look at them and flag if they are valuable. Valuable can mean different things. In the case of code generation is, for example, semantically equivalent to the reference code. You get a percentage that is, for example, 35% are valuable. And then in the paper, you can claim, okay, we got 20% of correct predictions, but keep in mind that among the wrong predictions, it's likely that we have something like 30% of valuable predictions. Okay, so there is more. Concerning the BLEU score, I don't know what to do with it, honestly. I mean, I report it in the papers that I work on only because it can be useful when you want to compare two techniques. Okay, and you say, okay, one get 0.8 of BLEU score, the other one 0.85. But more than that, I don't know what to do. It does not tell me a lot. I can also point you to the fact that there is a paper. I'm not sure it's published. For sure, it's on archive, where the authors presented CodeBLEU, that is a metric that is similar to BLEU, but is tailored for similarity between pieces of code. Okay, and what they show is that their metric aligns better with the developer's perception of code similarity as compared to the BLEU score. So if you need to compute the BLEU score on code, use CodeBLEU. They have an open source implementation. You can use it. Okay, it works and it's very nicely written.
Well, thank you, Gabriele. I think we are on time. I would like to thank you again for this great talk, and hope to maybe have you again in Brazil in the next edition of CIBSoft, maybe this time physically here in Brazil.
I hope so, and thanks a lot for inviting me. It was really a pleasure, and thank you all for listening and for the questions. It was an interesting discussion.
Okay, Gabriele, so see you next time.
Okay, see you. Thanks a lot.
See you. Thanks a lot. Bye.
Bye.